Hello everyone. In today's lecture, we are going to solve a couple of exercises related with the finite state machines, counters and the registers. These exercises is actually going to give you a brief understanding of how we can come up with a solution for different types of problems. And I think it's a useful practice for you to go through them and solve them individually as well. So let's give a start. The first exercise, it says would like to have the following register transfer operations in no more than one clock cycle each. Show how it could be done by drawing a register transfer diagram. So it's asking us to draw a register transfer diagrams based on these register operations. If you look at these, RB, register RB is copied into RA, RC is copied into RB, and RC is also copied into RA. And it's asking us to be no more than one clock cycle for each operations. So if we consider this, we need to consider them as 3 blocks. Okay, and these 3 blocks are going to be copied one into each other. So RB, for example, is copied into RA, RC is copied into RB, and RC is also copied into RA. Now, as RC is copied into RB and RA, what we can say is, let's say this is RC, this is RB, and this is RA. Now, as these are registers, what we can say about the registers, they have got the common clock, the dynamic input, and the output of one of the registers is connected to the input because we want to have the transfer of RC into RB in one clock cycle. So that's done. Now, RB is transferred into RA and RC is also transferred to RA. So these two statements are transferring the register's data into RA's register. Now, we have to choose one at a time. So we cannot have both at the same time. So what we can do, we can have a multiplexer over there that will be fed in. And one of the inputs are coming from RB and the other one is coming from RC. Okay, so based on that, each clock cycle we are going to fit one of these or copy one of these registers into the other one. I think this is pretty straightforward on showing how we can copy or register transfer operation from one register to the other. This was exercise 1. So we can also see the solution over here, which we have drawn already. It just shows the example. Now, the next exercise is draw the logic diagram of a 4-bit register with mode select inputs S1 and S0, and the register is to be operated according to the function table below. Now, we have got a 4-bit register with mode selection inputs. Now, the 4-bit register means we have got 4 flip-flops all together. So, flip-flop 1, flip-flop 2, 3, and 4. Let's say this is Q3. This is Q2, Q1, and Q0. Dynamic input clock for each, and they're all connected together so that we have got the clock input. Now we have got the inputs. So in the 4-bit register, we are just using D-type flip-flops. And now it says we need to make a selection between the modes. To do a selection, the easiest way of doing this is using a multiplexer. And as we have got two select lines and 4 different operations, we need to use 4-to-1 multiplexers, which is fit into the D. And each of these is going to be fed with 4-to-1 multiplexers. So we have got 4-to-1 multiplexer for each of these flip-flops. Now, based on these operation table, we have to make the connections required. So 0, 0, 0, 1, 1, 0, 1, 1. And all the select lines of the multiplexers are common and they have to be connected. And we can have S1 and S0. So 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Now, S0 and S1, when both are 0, that means register operation is no change, so it holds the previous value. To do that, we need to take the value, the previous value, and put it over there. And we need to do that for each of these registers. So when select is 0, 0, we are just feeding the same values in. When it is 0, 1, it has to be complement output. Complement output is Q primes. We already have the complement outputs on the D-type flip-flops, so we can just use these and fed in over there. So that's our second input of the multiplexer when the combination is 0, 1. And we have got that covered. Now the third one, which is 1, 0, is going to be load parallel data. We need to have a parallel data loaded into the circuitry. And this is coming in 1, 0, so that means that's going to be D3, D2, D1, and D0. So we have got the parallel inputs. And the last one, which is 1, 1, we need to clear the register to 0. So that means we have to fit in constant 0 to clear the register. And that is coming with zeros. And this diagram represents a 4-bit register with the mode selection. So if you have any questions related to these, note them down and you can ask me during the QA session. And the solution given over here, it's again, it's a multiplexer, but it's just using AND gates and the OR gates. So I prefer to use this multiplexer notation, which I believe it's easier to represent the logic itself. And this is designed for a 1-bit, you need to extend that to 4 bits. Next exercise is an FSM example. So, just a second, let's clear the page. It says the given synchronous tester equipment works as follows. We have got set of inputs, measure vectors, expected vectors, and the start, and we have got set of outputs, test fail, random error, and oscillating error. And we have got a couple of statements that we need to read it carefully, one by state by state, and understand them and identify what is actually required from us. This is the only way of solving these. So now let's look at it. It says the measured and expected vectors are fed to this tester serially 1 bit at a time, and 1 bit from each stream is compared against the other per clock cycle when the start input is asserted. So that means in this circuitry we have to check if measure vector and expected vector. So we have to check measure vector versus expected vector. And it says when the start input is asserted, we have to compare them. So we can say that if start is 1, check MV versus EV. That's what the first statement tells us. And this is happening per clock cycle. This is important because we are going to use that. So when a mismatch is found, the random error. So random error, RE, is going to be happening when a mismatch is found. So RE is going to be 1 when measure vector is not equals expected vector. That's the first thing it says over here. Again, output is asserted to 1 at the next clock edge and is deasserted at the clock edge when there's a match again. So that means RE is equals 0 when MV equals EV. So we don't get any error output when there's a match. And the last thing it says, RE output is inactive 0 as long as start is 0. So we can say that if S is equals 0, then RE is also 0. So the second statement done. We analyzed up until here, so second paragraph is done. The third paragraph, oscillating error. So oscillating error OE is asserted 1 at the clock edge when there is a mismatch followed by a match immediately followed by another mismatch. So what we can say is OE is 1 when mismatch followed by a match followed by another mismatch. So this should be the cycle for or the oscillating error that we need to have. And when there's a match cycle between two cycles of the mismatch, we need to raise oscillating error output to be 1. It is hence asserted at the next clock edge whenever such a sequence is observed, and deasserted when there is no sequence. So OE is equal 0 when no sequence. And the sequence that we are looking for is this. Okay? Mismatch, match, mismatch. Then OE output is inactive as long as start is 0. So again, if start is 0, then OE is equals 0. So that's also done. So third paragraph, we are done. The fourth one, when the start is deasserted 0 again, and the test fail output becomes 1 at the clock edge if there was any mismatch during the test run. So we need to have test fail to be 1 when start is 0 and MV not equal EV occurred in that cycle or in the test run, it says. And once asserted, TF stays 1 as long as start is 0. The test starts by resetting test fail to 0 when start is asserted. So that means if start is 1, then test fail is equals 0. So what I suggest you to do is, I suggest you to write these down, the statements as analyzed, so we know when it's going to what happened, and based on this we can easily derive our state diagram. So let's see what the question is asking. Is this a Moore or Milli machine? Why? So what do you think? Is this a Milli or Moore machine? What do we know? The Milli machine, the output depends both the present input and the state. With the Moore machine, the output only depends on the states. So if you read that carefully, you will see that each of these transitions are happening with the per clock cycle, or let's say at the clock edge, or where was it? Clock edge again, and the clock edge. So what is actually saying us, it's going to change the output whenever the clock is going to change, not the input. So that means this is actually saying us that the registers that we are having is a flip-flops, and when that register is activated, the output is going to change. So that means our state is going to change, and when the state is changed, the output is changing only. So that means this tester machine is going to be a Moore model or Moore machine. So as everything is working with the clock edges, so when the output is going to change when the state is going to change, not with the present input, we can say that this is a Moore model or Moore machine. Then it asks, draw out the state diagram clearly for the operation of the above tester, starting at state 0 with start equals 0 initially. Show the inputs and the outputs in your diagram. Try to have minimum number of states. Okay, I think it's pretty clear of what it's asking to us. We need to derive a state diagram. But first, I suggest you to note these down so you can easily follow it from the state diagram, or you can just directly follow from the paragraph given to us. Now, let's open a new page. And let's do this together. So before we start, we need to note down the inputs and the outputs. So let's start with the inputs. So inputs are, in this case, we have got the start, measure vector, and expected vector. These are our three inputs. Then the outputs are going to be random error, oscillating error, and test fail. So these are the three outputs that we need to consider. And based on that, we are going to derive our state diagrams. So if we look at over here, it says start with the state S0. Okay, and when we think about this state, as this is a Moore machine, the output is going to change with the state. So the output order that I'm going to use is RE, OE, and TF. And we know that when start is 0, so that means input is 0 over there, start is deasserted. As we already said, as long as start is 0, RE is 0, OE is 0. And of course, at the beginning, test fail is 0 because we don't have any mismatches. So that means we have got 0, 0, 0 as an output over there. Now, with this state diagram, we have two directions that we need to go. One for the match and one for the mismatch. So let's start with state 1. And let's say start is asserted and measured vector equals to expected vector. So start is asserted, measured vector equals to expected vector. That means we don't have any errors. We don't have any fails. So the output is 0, 0, and 0. On the other hand, we need to have state 2 where we will have start asserted but a mismatch. So start MB not equals EV. So when there is a mismatch, as it says the random error will be 1. So the random error is the first output, so it's going to be 1, 0, and 0. We don't have any oscillating error or test fail outputs to be 1. Only the random error. Okay, so we derived the two directions that our states are going to go. Now, the next thing that we need to consider, if we have a match, we are in state 1. If we are in state 1 and we have got another match, we have to wait over here. That means we are still satisfying that state. Okay. Now, if there is a mismatch, that means from state 1 we have to go to state 2 to raise the flag. Okay, we have got a mismatch, random error. So that means we have to make a transition when the start is 1, MV not equals EV. Okay, that's fine. The next thing that we need to consider, what happens if the start is deasserted when we are in S1? When the start is deasserted, as you can see, we need to go back to state 0 because start is deasserted, it's not gonna do any operations. We have to go back to the reset state and wait over there. So those two conditions are satisfied the same state. How about S2? S2, this is not the case because we need to know that the test failed output is going to be 1 when start is deasserted after the mismatch. So as we have got a mismatch over there, we need to have an extra state somewhere here to turn on the test fail output, which I'm going to do that later on. Another thing that we need to consider, how about if we have a match when we are in state 2? We cannot go back to state 1 because we need to satisfy the oscillating error. So oscillating error is saying us mismatch, match, mismatch. So that means we have to look for a match and then a mismatch to have an oscillating error. If we go to S1 and then it's gonna go back to S2, we will never ever get into that oscillating error state. So that's why we cannot go back to S1. In that case, we need to create another state over here, S3. So S3 is going to actually tell us that start is asserted and we have got a match after mismatch. So that means, again, we don't have any error, so the outputs are 0. And when we are in state 3, if we have got a mismatch, that means we are going to satisfy the oscillating error. To satisfy the oscillating error, we can actually have another state, which is S4. And we can say that this is start, measure vector, mismatches, expected vector. So in this case, we are going to set the random error to be 1 because we have got a mismatch, but also the oscillating error as we have got mismatch, match, mismatch sequence over there. So that means random error is 1, oscillating error is 1, test fail is 0. And we have got the state 4. Now, if we have got a mismatch when we are in S4, we have to go back to S2 and repeat this sequence. So S MV not equals EV will take us back to S2. And if there is a match, we need to go to S3. So S MV equals EV. So when there is a match, go back to S3 and so on. Now, if we are in S3 and if we have got a match, what will happen? So if we are in S3 and we have got a match, we need to think about it. So what do we need to think about it? As we have got a mismatch and a match, and the mismatch which is a pattern, if we got a match again, it's gonna be mismatch, match, match, and the mismatch, we are breaking the pattern over here. So that means we need another extra state to have for the matching state. So S5 is going to be 0, 0 as an output because we have a match again. So S MV equals EV. Now, as we have got a match, this is out of this sequence because that sequence is mismatch, match, mismatch. This is out of it and we are satisfying the condition. Now, when we are in S5, if we have got another mismatch, we need to go back to S2 because we are breaking the sequence over there. So that means that has to go back over here and we can say that S MV not equals EV. So there is no mismatch, there's a mismatch, so we have to go back to S2 and start again. Now we have got 5 states over here. That's all checking these conditions: oscillating error and the random error. The next thing that we need to check is the test fail. So test fail is only happening when we have got a mismatch during the test run. So mismatch is happening all on these S2, S3, S4 and S5 states. S1 doesn't have any mismatches, that's why it's going back to S0. But these ones, as they got a mismatch in 1 or 2 cases, we have to consider another extra state, let's say S6 over here, which it will say that start is deasserted. So we can go from S5 when the start is deasserted. We can go from S3 when the start is deasserted. We can go from S4 when the start is deasserted. We can also go from, I'll take it from here, and from S2 when the start is deasserted. And from S6 we know that output random error is 0. The oscillating error is 0 because we don't have any oscillations. The only thing that is going to be 1 is a test fail because it's satisfied, the start is deasserted, test fail output becomes 1 at the clock edge if there was any mismatch. So on the mismatches cases, when the start is deasserted, we go to S6. Now, when we are in S6, if the start is 0, we wait over there. If the start is 1 and we have got a match, that means we'll go back and start again. So start MV equals EV. We'll start back from state 1. We have got a match and ready for the next sequences. And if we are in S6 and we have got a mismatch, that means we have to go to S2, which again satisfies that condition. So start MV not equals EV will start from S2 and we have to start from checking each of these sequences again. So I think that's all that we need to draw for a state diagram for this tester machine. And you can, I know it's quite messy over here, but you will find the proper version in this the next slide over here. So if you have any question about how we draw this state diagram, note it down and you can ask me during the QA session. Then the next question that is asked, what will be the minimum number of flip-flops needed to store your states? And what will be the number of flip-flops required with one hot state assignment? Now, so what we can consider over here, if we are going to use binary states, as we have got state 0, 1, 2, 3, 4, 5, 6. So we have got in total 7 states. To cover 7 states, we need to have 0, 0, 0 up to 1, 1, 0. Right? So over here, we can have flip-flop A, B, and C. As we need to cover 6 states, 7 states over here, we need 3 flip-flops for ordinary binary state assignment. If we are going to do one hot state assignment, we have got S0 to S6 7 states, and each of these states is going to be turn on one flip-flop at a time. That means for one hot we need 7 flip-flops, one flip-flop for each state. I think this is clear. So you can see the solution for the state diagram over here, and you can also see the solution for the flip-flops that need for ordinary binary assignment or for one hot state assignment. And that's the end of exercise 3. Now the last question it is asked is exercise 4, synchronous rising edge triggered 4-bit wraparound up counter. So in this question it says we have got a 4-bit wraparound up counter which has got a synchronous reset and parallel load inputs, and the condensed state table for the up counter is specified as follows. So we have got the reset, load inputs, and the clock. They're all synchronized, and we have got the parallel load inputs and the parallel outputs. So before we get into the details of it, let's draw the block diagram of it. So we have got the clock, the reset input, and we have got the load input. We have got 4 parallel outputs and 4 parallel inputs. So D3, D2, oops, we cannot write over there, D1 and D0, Q3, Q2, Q1, and Q0. This is what it's asking us. We have got 4 parallel inputs and outputs, and we have got the load input and the reset and the counter, the clock. So with the reset is 1, no matter what is happening, the output is always going to be 0. Okay. And when reset is 0, load is 1, we are loading new data from the parallel inputs. And when the load is 0, we are just doing a counting. Okay. Now, let's read this statement given to us. This counter will be used in a skipping sequencer application where the machine output numbers in decimal sequence 0, 1 up to 15. So that means we can go from 0, 0, 0, 0 up to 1, 1, 1, 1. And whenever we reach to 1111, it will just wrap around and start again. So this is called a wraparound up counter. And it says except the counts that have twice the value of the odd numbers are skipped. So the counts that have the twice the value of the odd numbers. So that means 1 odd number twice is 2 will be skipped. 3 odd number twice is 6 will be skipped. 5 odd number twice is 10 will be skipped. 7 odd number twice is 14 will be skipped. So from 0 to 15 we have got 2, 6, 10 and 14 which is going to be skipped. And this is also stated over there. The skipping sequencer inputs and the outputs are depicted in the below figure. Add minimal combinational logic around the provided up counter to implement this skipping sequencer. Show your implementation by drawing out the up counter, your added logic and the connectivity of all signals. You do not need to show the internal logic. Okay, so if we get into the details, let's say we start from 0, 0, 0, 0, 0, 0, 0, 1. When we have got 0, 0, 1, the next one is 0, 0, 1, 2, which is 2, but we want to skip that one. So to skip that one, we need to go to 0, 1, 1, 1. That means we are jumping there. Then we carry on 0, 1, 0, 0, 0, 1, 0, 1, 5, 0, 1, 0, 0, oops, sorry, 0, 1, 1, 0. Now we have to skip 6. To skip 6, that means we have got 4, 5, 6, and 6 needs to be skipped, and then we go to 1, 1, 1. So over here, from 0, 1, then it's going to be jumped from 5 to 7, 6 will be skipped. Then we carry on 8, 9, 10, 11. Again, as 10 is in the skipping sequence, that means this is going to be skipped, so we have to jump from 9 to 11. Then we carry on 12, 13, 14, and 15. Again, we need to skip 14 and we have to jump from 13 to 15. Now, how are we going to derive the logic based on this? If you look at it, what is happening is this is Q3, Q2, Q1, and Q0. Now, on these two, you can see that, okay, the Q3 and Q2 is incrementing, but Q1 and Q0 can be used to detect when do we need to skip, because it's always 0, 1 condition, and it always jumps to 1, 1. Again, 0, 1 and jumps to 1, 1. So this satisfies for each condition, for each sequence that we need to have. So this is actually making our lives easier. Now, what we need to know about is when we detect 0, 1, we have to load new data rather than incrementing the counter. So we start with 0, 0, then the counter increments, load is 0. When we are in 1, okay, 0, 1 is detected. That means we have to load a new value rather than counting to 2. So to skip that, we have to initialize, we have to set the load to be 1 so that we load 0, 0, 1, 1 in there rather than counting to 0, 0, 1, 0. To do that, as we have got Q1 and Q0, we need some kind of logic circuitry to turn or to set the load to be 1. So that load is going to be 1. How do we do that? We can actually go and check using an AND gate. So this is going to be 1, but Q1 has to be also 1, so that's why we use inverter. So we can say that when Q01 is detected, when both Q0 and Q1 is detected, we have to load a new value. So we can just use inverter and AND gate over there, and we can activate the load function. Now, the other question that we need to ask, okay, we load it, okay, we set the load to be 1, we are expecting a data to be in. But we know that no matter what is happening with D3 and D2, because this is always going to increment it, only D1 and D0 is going to be 1, 1. 1, 1, 1, 1, 1, 1. So we can just set these two together to be 1. And actually, I can use that from the load, because when load is 1, we are going to load a new data, and that new data, the least significant bits are going to be always 1, 1. Okay? So at the beginning, we start with 0, 0, 0, then the counter starts when the load is 0, it increments to 1. When 0, 1 is detected, that's going to activate the load to be 1. When load is 1, we load D1 and D2 to be 1, 1, so we skip to 0, 0, 1, 1. Now, how about Q3, Q2, and D3, D2? As these are not going to change, we can just directly connect these back into their inputs, like a feedback path. So these are all going to be incremented throughout the counter, but these are always going to be set to 1. So this is going to be 0, 0, 0, 1, 1, 0, or 1, 1, but this is always going to be load these values, the skipped sequences. So that's all you need to know about the skipping sequencer. And this is a diagram that we need to have, the external logic that we need to have, and these connections. In the next slide, you will see clearly how this is done. And the last part, it says, will your implementation of the skipping sequences recover back to its normal sequence of outputs if it ends up in one of the forbidden states, 2, 6, 10, 14, due to noise? And how many clock cycles will it take? Okay, in any cases that we ended up in, let's say, in 6 or maybe in 10. As this is a wrap up counter, this is going to go from the noise to the next upper value, which is a valid value, which is 7. And if it is 10, it's going to be 11. If it is 14, it's going to be 15. Or if it is 2, it's going to be 3. So this can be done in one clock cycle, because as it's going to count up, each count is going to take one cycle. So on the next clock cycle, it's going to be 3. On the next clock cycle, it's going to be 7 or 11 or 15. So we can say that it will take one clock cycle for the skipping sequencer to recover back to normal sequence. I think that's the end of exercise 4. You can see the complete diagram of the skipping sequencer. The last two digits, Q1 and Q0, inverted and ended, so it's activate the load input. When the load input is activated, both of them are going to be set to 1. And when this is 1, we are skipping the sequence, and this is just incremented with the counter itself. Again, it takes one clock cycle to recover back to normal sequence, 2 to 3, 6 to 7, 10 to 11, and 14 to 15. So if you have any question, note them down, and you can ask me during the QA session. That's the end of chapter 7. Thank you.